let's take a look at this supplement, 2.8. So I can find it in my notes. So we've pretty much covered everything in 2.8. We just got a little bit more. So we're going to talk about higher order derivatives for a minute. And I alluded to this higher order derivatives in our lectures on 2.8. And now we're going to delve into it formally. Okay. So the top of your handout says if a differentiable function, if f is a differentiable function, then its derivative, f prime, is also a function. Right? F of x is a function of x. F prime of x is a function of x. So f prime may have a derivative of its own, and we denote that derivative by f double prime. Okay? So f double prime is the derivative of f prime. Okay? The new function, f double prime, is called the second derivative of f because it is the derivative of the derivative of f. The third derivative, then, of f is denoted with f triple prime. Okay? And it is the derivative of the second derivative. So, as an example, f of x equals x squared minus 6x plus 10. We've got to find the third derivative just using the knowledge that we have now. Okay? And so in our 2.8 lecture notes, right, you were given a function f of x equals 2x minus 6, and using the definition of a derivative, we showed that the derivative of f of x, f prime of x, is equal to 2. We also showed, using the definition of a derivative, that for the function g of x equals x squared minus 6x plus 10, that its derivative is equal to 2x minus 6. Okay. So I have changed the name of the function in this example. In this example, f of x is now what g of x was in your notes. X squared minus 6x plus 10. And so we know the derivative of f of x from previous work in section 2.8, right? Using the definition of derivative, f prime of x is equal to 2x minus 6. This is a differentiable function. It has a derivative. And so the derivative of f prime of x, which is the derivative of the derivative of f of x, we know the derivative of 2x minus 6 is 2. Okay. So you can differentiate a derivative. Okay. Now, the graph of f double prime of x, right, the second derivative of f of x, is a what? Horizontal. Yeah, horizontal line. It's equal to, right? This is the graph of it is the horizontal line y equals 2. What's the slope of a horizontal line? 0. Slope is 0. And the derivative function gives you the slope of the curve for each value of x, right? So what's the third derivative going to be? 0. because the slope of the horizontal line is 0, so the derivative of this function is going to be 0. Because the derivative is the slope of the function at each value of x. Okay. Okay. Down below, we have done examples, right, where a ball is thrown up in the air, and h of t is the height of the ball at time t. Okay, the ball is thrown vertically into the air. So the derivative, right, we did an example of that in class where we had to find the instantaneous velocity of the ball at t equals 2 seconds. So the derivative of h of t, which we denote with h prime of t, right, that gives us the velocity of the ball as a function of time. And so we'll use v of t. We'll often use v of t to represent the velocity. And the velocity is a function of time, and that's equal to the first derivative, h prime of t. Acceleration, right, how fast the speed of the ball is changing. Okay, we represent that as a function of time, and acceleration is the derivative of the velocity, v prime of t. And v prime of t is the derivative of h of t, so acceleration is the second derivative of h of t. Okay? H of t gives us the position or the height of the ball. The derivative of h of t gives us the velocity. And the second derivative of h of t gives us the acceleration as a function of time. Okay? All right. Any questions on that? Okay. So we're going to talk now about there's different notation for a derivative in mathematics. Okay. Sir Isaac Newton gets most of the credit for the development of calculus, but there was a guy in Germany who was developing it at roughly the same time. His name is Leibniz. Is how I pronounce it. Okay. It's German. I took 2 years of German, but I can hardly speak a word of it. Okay. And so he had his, communication back then wasn't like it is today. Okay, they didn't get it was a long walk from Germany to England. Okay, and so he had his own notation for derivatives, and so we're gonna, and a lot of that notation we still use today, right? A lot of mathematicians favor this guy's notation over what we've been using. Okay, so if we have the function, right, y is a function of x. Y is equal to f of x, then we know the derivative of f of x, we denote that with f prime of x. But what Leibniz used was, to denote the derivative of y, he used this notation right here, dy over dx. And that's pronounced the derivative of y with respect to x. Okay? The second derivative, right, which is the derivative of the first derivative. The second derivative, so this is the derivative of the first derivative, and that is denoted with this notation here. This is the second derivative of y with respect to x. So it looks like they're squaring the d, because we get d of d, and then it looks like we're squaring dx on the bottom. So what this is saying up here is the derivative of the first derivative equals the second derivative. It's saying derivative of the first derivative equals the second derivative. And that's how we denote that using Leibniz notation. Okay? And we'll be using a lot of that going forward. Okay. All right. In the table below, kind of summarizes the various kinds of notation for derivatives. And it points out here, right, d over dx is read the derivative of. I was always taught to read it as not just the derivative of y, but the derivative of y with respect to what variable? Okay, what's the independent variable? So we read d over dx as a derivative of, just as you read this symbol as the square root of. Okay. And so for the first derivative, right, y is a function of x, the various forms to represent the first derivative, f prime of x, derivative y with respect to x. This is also derivative of y with respect to x. And this is derivative of f of x with respect to x. And if that wasn't enough, you know how we use prime in representing the derivatives of functions like f of x, g of x, and h of x. You can also represent the first derivative with y prime. Okay. So that is pronounced y prime. Those are primes and not ones. Okay. And then second derivative, f double prime of x, second derivative of y with respect to x. This is the derivative of the derivative of y with respect to x. And this is the second derivative of f of x with respect to x. And then you can also write the second derivative as y double prime. For the third derivative, right, when we have f of x, g of x, h of x, like that, right, we usually use 3 primes to represent the third derivative. This is the third derivative of y with respect to x. This is the third derivative of f of x with respect to x. And then we have y triple prime. Once we get to the fourth derivative and higher, we use just numbers, right, and positive integers to represent the derivative. So this is the fourth derivative of f of x. This is the fourth derivative of y with respect to x. And then, I didn't put it on here, but for the nth derivative of y equals f of x, okay? This is for n, right, greater than or equal to 4. Okay? We have f, right, so this represents the nth derivative of f of x. And this is the nth derivative of y with respect to x. And then this is another way of writing the nth derivative of y. Okay. So various notations, right, for higher order derivatives, okay, and just by sheer repetition, right, you become familiar with them all this semester. So any questions on notation for higher order derivatives? Okay. All right, so now you can get out your notebooks. And this will be, this is where we'll start learning the shortcuts that you replicate. But if on an exam it says, find the derivative of this function using the definition of a derivative, then you got to do the limit. Yeah, you can't do the shortcut. But you can use the shortcut to see if you got the right answer. Right? Yeah, it's a good backup. All right, so this is section 3.1, and we are learning differentiation laws starting today, right? So this, all of chapter 2, with the limits that we were doing, it was just so we could get to this definition of a derivative. everything we've done this semester was just so we could get to that. Okay? And now that we know the definition of a derivative, you probably won't see another limit. I don't want to say you won't see another limit, but you won't probably see very many of them until the final exam. Okay? Now watch me eat my words. Alright, so this is section 3.1. And we're going to be learning different, we're going to learn differentiation laws, right? And there are several of them. Okay? So the first one is called the derivative of a constant function, or a constant. So I have the constant function f of x is equal to c, okay? And so a constant in this class is just a real number from the real number line, okay? Well, the derivative of a constant, a real number, is 0. And we just talked about that in an example, right? Where the function was equal to the real number. The graph of that function is a horizontal line. The slope of a horizontal line is 0. Okay. So f of x equals c. Its graph is a horizontal line. Horizontal lines, all horizontal lines have a slope of 0. So the derivative being equal to 0 makes sense. Okay. So some examples, a couple examples. If my function is f of x equals 10, right? Then the derivative of f of x which is equal to the derivative of the number 10 on the right hand side is 0. If I have y is equal to 2 times pi, right? So remember y and f of x, right? Y equals f of x. So I can have y on the left hand side of f of x. If y is equal to 2 times pi, then the derivative of y with respect to x is equal to the derivative of 2 times pi with respect to x. Pi, you know, is a constant, like 3.141. We'll double it, get another constant. Derivative of that constant is 0. The second rule is the power rule. If n is a real number, then if n is a real number, then the derivative with respect to x of x to the n power, you take the exponent n, you bring it down in front of the x, and then you subtract 1 from the exponent. So you got to remember from your algebra, remember f of x equal to x to the n is called a power function. So we're differentiating the power function. Okay. So examples, f of x equals x squared. Okay. Then the derivative of f of x, which is f prime of x, is equal to the derivative of x squared, and the derivative of x squared is 2x, right? Bring the 2 down from the x, subtract 1 from the exponent. Now, while we're defining the differentiation rules, we're going to be doing all of this derivative with respect to x on the right-hand side. But eventually, once we know the rules, we'll be able to go from here to here. Okay? Just like when we did the rules of limits, right? We knew you take the limit inside the square root. We're up in the, put 1 in the numerator, 1 in the denominator, and all this stuff. But you didn't have to actually explicitly write it down once you knew the rules. Okay. All right. So g of x is equal to x to the 99th power. So g prime of x is equal to the derivative with respect to x of x to the 99th power. You bring the exponent 99 down from the x, and then you subtract 1 from the exponent. So derivative of x to the 99th power is 99 times x to the 98th. If I have h of x is equal to 1 over x to the 8th, you think just keeps falling down, doesn't it? Is this 1 over derivative is 1 over 8 times x to the 7th? So you can, yeah, this is not, derivative is not 1 over 8 times x to the 7th. You got to rewrite this as x to the minus 8 power. Now you can use the power rule. Okay. And so the derivative of h of x is the derivative with respect to x of x to the minus 8. And now you bring the exponent down, subtract 1 from the exponent. And that's the derivative. Okay. All right, and then to simplify, you could write this as minus 8 over x to the 9th. Okay. Which one do you put on an exam? Depends what the instructions are. If it says you don't have to simplify, then you don't have to simplify. If you have to simplify, then you got to simplify. Okay. All right. Y equals the square root of x. What's its derivative? Well, you know square root of x is x to the 1/2. So the derivative of y with respect to x, bring the 1/2 down from the x, subtract 1 from the exponent, you have 1/2 times x to the minus 1/2. gotta simplify. This is 1 over 2 times x to the 1/2, which we write as square root of x. Any questions? All right, the next rule is called the constant multiple rule. If C is a constant, which is a real number, and F is a differential pole function, then the derivative with respect to x of C times f of x. Okay? So we're just taking the function f of x, and we're multiplying it by a real number to create a new function. Okay? That derivative, right, this C is just a multiplicative constant. It can be brought up from the derivative side. It is equal to C times the derivative with respect to x of f of x. So examples. We have y is equal to 3 times x to the 4th. Then the derivative of y with respect to x is equal to the derivative of 3 times x to the 4th. And by the rule, by the constant multiple rule, 3 is just a multiplicative constant. It can be brought up from the derivative sign. So we have 3 times the derivative with respect to x of x to the 4th. And the derivative of x to the 4th is 4x cubed from the power rule. And 3 times 4 is 12. So the derivative with respect to y, or the derivative of y with respect to x, at 3x to the 4th, is just 12x cubed. In the next example, we have f of x is equal to 6 times the cube root of x squared. Well, first thing we got to do is rewrite the cube root of x squared. Cube root of x squared is equal to x raised to what power? What is it? 1/3? 2/3. X squared, you take the cube root of x squared, right? And so, the derivative of f prime of x is the derivative of 6 times x to the 2/3. And by the constant multiple rule, I can bring the 6 up front of the derivative. And so I have 6 times the derivative of x to the 2/3. Derivative of x to the 2/3 with respect to x. So by the power rule, the derivative of x to the 2/3 with respect to x is 2/3 times x to the minus 1/3. And 6 times 2/3 simplifies to 4. We'll just leave it as 4 times x to the minus 1/3. Any questions on that? All right. The next rule is the sum rule. It says if f and g are both differentiable, then the derivative with respect to x of f of x plus g of x, right? We're taking the sum of 2 functions. And the derivative of f of x plus g of x is the derivative of f of x plus the derivative of g of x. So as an example, we have y is equal to 3 times the square root of x plus 2/3, or plus 2, yeah, plus 2 over x cubed. Okay. So we have, right, it's like the sum of 2 functions. And so the derivative of y with respect to x is the derivative of 3 times the square root of x plus the derivative of 2 over x cubed. Okay. Well, we got to rewrite this before we can differentiate it. Okay. So square root of x is x to the 1/2 power, and 2 over x cubed is 2 times x to the minus 3 power. And now we can differentiate this. Okay. The derivative of y with respect to x is the derivative of 3 times x to the 1/2 power plus the derivative with respect to x of 2 times x to the minus 3 power. Well, in this first derivative, the 3 can be brought out. 3 is a multiplicative constant, so I bring it up in front of the derivative. And then I have the derivative with respect to x of x to the 1/2. We use the power rule to find that derivative. Bring the 1/2 down front. subtract 1 from the x bar. So this is equal to 3 times 1/2 times x to the minus 1/2. And then finding the derivative of 2 times x to the minus 3 power with respect to x. Bring the 2 out front of the derivative. And just take the derivative with respect to x of x to the minus 3 using the power rule. So we have plus 2, and the derivative of x to the minus 3 power is minus 3 times x to the minus 4 power. Okay. Well, 3 times 1/2 is 3/2. And 2 times minus 3 is minus 6. So we have the derivative of our original function is equal to 3/2 times x to the minus 1/2 minus 6 times x to the minus 4 power. Any questions on these rules? All right, and if you have the sum rule, then there's got to be the difference rule. And the difference rule is like the sum rule, except you're taking the difference of two functions, right? If f and g are both differentiable, then the derivative with respect to x of f of x minus g of x is equal to the derivative of the first function, f of x, minus the derivative of the second function, g of x. All right. So let's do some examples. So in the first example, g of x is equal to 4x cubed minus 5x squared plus 3x plus 10 over x. Well, we got some rearranging to do before we differentiate this function. What do we have to do you think?
H part by x.
There you go. Brian, you hit it head on. Right? Each term in the numerator has to be divided by x. Okay. So 4x cubed over x minus 5x squared over x plus 3x over x plus 10 over x. Oh, what I forgot to note, in these examples, we are combining all of the rules thus far. Okay? So, g of x can be written as 4x squared minus 5x plus 3 plus 10 times x to the minus 1 power. So actually we have a sum and difference of functions now, right? Each term can be thought of as its own function. Okay? And so we're adding 3 functions and subtracting 1. And so we can apply the sum and difference rule, right, to each term. And then to each term apply the appropriate rule to find its derivative. So g prime of x is equal to the derivative of the first term minus the derivative of the second term plus the derivative of the third term plus the derivative of the last term. So finding the derivative of the first term, right, we use the constant multiple rule, right, plus the power rule. And we get the derivative 4x, right? The 4 is just a multiplicative constant we carry along. The derivative of x squared is 2x. Derivative of the second term, right? We just carry the 5 along, so we have minus 5. What's the derivative of x equal to?
0.
Is it 0?
That one's.
The derivative of what?
What's the derivative of x?
Yeah, it'd be 1.
It'll be 1, right? Yep. F of x is equal to x. Place f of x with y. Y equals x. Graph y equals x, right? Is the 45-degree line that goes through the origin, and it has a slope of 1. So the derivative of x is just 1, and so the derivative of 5x is 5. And the derivative of minus 5x is minus 5. Derivative of the constant 3 is 0. And the derivative of 10 times x to the minus 1. Again, we just carry the 10 along. And the derivative of x to the minus 1 is minus 1 times x to the minus 2, right? By the power rule. And now let's clean it up a little bit. Four times 2x is 8x. Minus 5 times 1 is minus 5, plus 0 is 0. 10 times minus 1 is minus 10. So we have minus 10 times x to the minus 2. Okay. Any questions? All right. In the next one, we have, next example, we have h of x is equal to x plus 2 times x minus 1. How do we find the derivative of that function? Well, we got to do some work first, right? Give me a word that describes what we got to do first. Acronym. FOIL, right? So we got FOIL first. So when we FOIL, we have h of x is equal to x squared plus x minus 2. So h prime of x, right, if this was a problem on an exam and you had to give the derivative, you don't have to do everything we've been doing. Derivative of x, right, we're just laying out the rules, the laws, and then you'll implicitly apply the laws like on an exam question. So you know derivative of x squared by the power rule is 2x, and the derivative of x by the power rule is 1, and the derivative minus 2 constant is 0. So derivative of h of x in this case, right, is equal to 2x plus 1. All right. So in the next exercise, you're going to tell me what the derivative is. I'll give you a minute to calculate. F of x is equal to 7x cubed minus 3 over the cube root of x squared plus 2x plus 5 squared. Actually, before you find the derivative, let's set this thing up together. Okay. We got to do some algebra, right? So f of x, 7x cubed, we know how to differentiate that. But now we have minus 3 over the cube root of x squared, right? How do we write 1 over the cube root of x squared? That's x raised to what power? It's negative 2/3, right? So let's do this step. Take a shorthand second to do that review. Okay. So we have the cube root of x squared we know is x to the 2/3. 1 over the cube root of x squared is equal to 1 over x to the 2/3, which we've written as x to the minus 2/3. Okay. So minus 3 over the cube root of x squared is minus 3 raised to the minus 2/3. What about this last term?
It's just 25.
25. 5 squared is 25. It's a trick question. Don't let it happen to you, because some students will bring the 2 down in front of the 5 and subtract 1. Right? I mean, that happens. This is a constant. 5 squared is 25. All right, now you find f prime of x. I'll give you a minute. Alright, Laura, what'd you get for the first term of the derivative?
Well, that would be 21x squared.
Right? Right, so we have a sum and difference of functions, right? So we can differentiate each of these terms, right, one by one, right? So derivative 7x cubed, carry the 7 along, bring the 3 down in front of the x, subtract 1 from the exponent, and you have 21x squared. Brian, what'd you get for derivative of second term?
2 over the cube root of x.
That's true. Yeah. So minus 3 times minus 2 is equal to plus 2, right? And when you subtract 1 from the exponent, minus 2/3 minus 1. Well, that's the same as minus 2/3 minus 3/3, which is minus 5/3. But Brian expressed this as 1 over the cube root of x to the 5th, which is a true statement. All right. Alex, what'd you get for derivative 2x?
2x. I did just get that one.
You skipped this one?
Yeah.
Okay. Yeah, you need that.
Yeah.
You just carry the 2 along.
Yeah. So just 2.
Just 2, right? Because the derivative of x is 1. I'll give you the tough one. What's the derivative of 25?
It's 0.
It's 0. Okay. Well, now let's find the second derivative. So now that we have the first derivative written on the board, all cleaned up. Find the second derivative. No, I apologize. You know how difficult, I mean, I've taught South, I don't know how many thousand students I've taught. And before I started teaching, I worked in industry, and I don't know how many thousands of people I met in industry. So I can't, my brain can't keep a catalog of names, so. Nico, Noah Key. So Cameron, did you find the derivative of the first term here, 21x squared?
Yes, sir.
What'd you get?
42x.
Say what?
42x.
42x, right? Carry along 21. Use power rule to differentiate x squared, bring the 2 down front. 21 times 2 is 42. And then subtract 1 from the exponent. Okay. Ethan, are you in here? Did you differentiate 2 times x to the minus 5/3?
Yeah, I've just got minus 5 over 3.
Just minus 5 over 3? Well, what you got to do, right? You carry the 2 along. You bring the minus 5 over 3 down front of the x, and then you subtract 1 from the exponent. That's the pattern, okay? So, is there anybody in here praying that I don't call their name? Okay? Because I know how that might feel. Leah, are you in here?
I am. Yeah,
Which-
I got that.
Which one? You're Leah in the
Yes.
yellow?
Yes.
What- What'd you get?
I didn't get to solving that, but I knew that I had to carry down the 5/3. It'll carry down the 2 down the
Yeah.
5/3.
So let's do this one together, right? So I'm finding the derivative of 2 times x to the minus 5/3. We carry the 2 is a multiplicative constant. Right. We bring the minus 5/3 down in front of the x, and then we subtract 1 from the exponent. And minus 1 is the same as minus 3/3. So minus 5/3 minus 3/3 is minus 8/3. And 2 times minus 5/3 is minus 10/3. Okay. Nelson? Yeah.
0 again.
I'll give you the tough one again.
Yeah, 0.
You got 0, right? It's plus 0. Okay. And so we don't write out plus 0. Okay. And so that's the second derivative. Okay.
So are we gonna be in like an infinite loop of derivatives because of this?
Oh, we're gonna talk about that in a second. Right? Because you are in an infinite loop of derivatives unless it's a polynomial. When you differentiate a polynomial, eventually all derivatives are 0. But that's the only case. Okay? Because whenever you have an exponent that's not an integer, right? The derivative of this is this, and the derivative of that is this. You never get to 0. Okay? When you just keep differentiating the next term. Okay. All right. And so, Stephen, that is a very timely question you just asked. Because in this next exercise, and I'll give you a minute to work it out, you're going to find the 4th derivative of g of x given g of x is equal to the polynomial 7x cubed plus 4x squared plus 2x plus 25. Okay. So you need to calculate g prime of x, g double prime of x, right, the 3rd derivative of g of x, and then finally the 4th derivative. Okay. And I'll call on people for each of those derivatives. Okay. I called Nelson last. Meredith. Okay, Meredith, what'd you get for the first derivative?
I got 21x squared plus 8x plus 2.
There you go. That's perfect, right? Derivative of 7x cubed is 21x squared. Derivative of 4x squared is 8x. Derivative of 2x is 2. Derivative of constant 25 is 0. Okay. Let's see. Steve, what you get for the second derivative?
I got 42x plus 8.
42x plus 8, right? Derivative of 21x squared is 42x. Derivative of 8x is 8. Derivative of constant plus 2 is 0. Okay, very good. See, Alex, I picked on you. Grace Hill.
I got 42.
Yep, right. Derivative of 42x is 42. And derivative plus 8 is 0. Lyra?
0.
Yeah, right. All you guys constant, right? Derivative of constant is 0. Okay. Now here's the interesting thing. Once one of the higher order derivatives equal to 0, all the higher order derivatives after that will be 0, right? Because the derivative of 0 is 0, right? The graph of this function is the horizontal line y equals 0, right? It's the x-axis. And the slope of a horizontal line, even y equals 0, slope of horizontal line is 0. Okay? So the nth derivative of x is 0 for n greater than or equal to 4. Okay? The fifth derivative, sixth derivative, seventh derivative, eighth derivative, ninth derivative are all 0. Okay? All right. So this alludes to Stephen's comment, but derivatives being an infinite loop, which can happen, which happens most of the time probably. The function f is a polynomial. If and only if the nth derivative is equal to 0 for some integer n. Now, how long it takes before the nth, how large n is, depends upon the degree of the polynomial. If the degree of the polynomial is 100, you got to do a lot of derivatives, right? So, all right. Derivative of the natural exponential function. This is like the easiest derivative of all to remember. The derivative of e to the x is just e to the x. Couple examples. Y is equal to 3 times e to the x. Okay. So the derivative of y with respect to x is equal to the derivative of 3 times e to the x. 3 is just a multiplicative constant. Pull it out from the derivative. You have 3 times the derivative with respect to x of e to the x derivative e to the x is e to the x. Okay. G of x is equal to 1 over x cubed plus the 4th root of x minus e to the x. Your assignment tonight is to find g prime of x. We'll compare answers first thing tomorrow. Okay. So I'll see you tomorrow.